More applications of linear regression. All right, so application number 2, we have a vending machine that has noticed that its change in price, in cents, so prices in cents, for its bottles of juice sold, weekly demand for juice of bottles changes. So again, as price changes, the demand for the juice changes. So this is a price-demand equation, all right, based on the data collected, but it's not a perfectly straight linear case. It's a close to. And so what we're going to do is we're going to use this information, this table of information, to find the best fit line for our demand. And so remember, the demand equation is quantity equals slope times price plus my y-intercept. And so quantity is the y value, so that goes in list 2. Price is the x value, that goes in list 1. So you go to your stat key, you do your list 1, list 2, and then we're going to go over to calculate. And you're going to pick the linear regression, ax plus b. Alright, and then when you do, so you can again carefully plot it in. We went over this in the last one, and I'll do one more example where I'll walk you through it again on the calculator at the end. Plug it in. You should get your slope comes out negative 9.2. Your y-intercept comes out 1200. So my quantity demanded is negative 9.2 times price plus 1200. And there's my best fit line. It's a pretty good fit. The R comes out pretty good, so 0.978, so it's a pretty good fit. All right, now we're going to use it. Now make sure you're careful. Remember, these are cents, so 35 cents, 45 cents, 55, 65, and then that's the number of bottles. In WebAssign, you've got to be careful. There's a couple problems where they do this, where they give you dollars even though price is in cents. And so you don't want to plug in 0.75, you want to plug in 75 cents. And that's what you're going to plug into the equation. So you're going to find the number of bottles of juice at 75 cents. So you plug that carefully in, and it comes out 510 bottles of juice are demanded at 75 cents. Next example. Alright, so we're given a table of the U.S. infant mortality rates and death per 100 live births for various years, so 1960 up to 1999. And so we're going to find the best fit line to predict the mortality rate based on this table. And then we'll get to why I asked the second part of this question. Is this a good fit? So remember, years are always going to be the x values, and we're always going to start year 0 as our starting point. So 1960 is our starting point, and then this would be the number of years after that. So 10, 20, 25, 30, 35, and 39, right? My x represents the years after 1960. Right? That's the first piece of information. I don't have any information before 1960, so that's times 0. And then every year after that. Alright, that's going to go in list 1. So the mortality rate's going to go in list 2. That's my y value, that's my x value. Then we go into the stat key. You go to calculate, and you're going to pick the linear regression ax plus b. Alright, so these come out not real pretty, but negative 0.5004. So I am going to just round that to negative 0.5. It's 004 x plus 4.657. Actually, if I round consistently, I'm going to round both to 3 decimal places. Alright. 3 or 4 decimal places, good rule of thumb on these. 3 is probably the smallest number of decimals you should have. 4 would probably be a good stat. 3 or 4. So there is my best fit line, and it's a pretty good fit. It comes out above 0.9. Alright, now the predictor. The year 2010. So the year 2010 would be 50 years after 1960. So 50 is what we plug in. And so the y comes out, and the reason why I asked the second part of the question, because my y value comes out negative 0.376. We cannot have a negative mortality rate, and so this is not a good estimator for 2010. The reason why is it's never a good idea to go out so far beyond the last piece of information I have. So there's two reasons it's bad. All right, first of all, my last year was 1990. This is 2010 is 11 years after my last piece of information. All right, which is problem one. The second thing is if you understand mortality rates, is that as technology and health services get better, mortality rates tend to slow down. But they never zero out, so they don't follow a linear path. They follow actually more of a logarithmic path. And so this is not really a good fit for this particular type of question. It's not a good estimator for that. Now, I could probably use it to estimate within the years 1960 to 1999, but I wouldn't want to go past 1999. So I could use it if I wanted to predict, something like 1965, which I don't have that piece of information, but that's well within my boundaries, right? It's well within my year. So I could use this line to predict any time between 1960 and 1999, but it's probably not a good idea to go past 1999, right? Especially 11 years past it. And sometimes that happens. So sometimes statistical information isn't always good, and it's especially not good to use it well outside its boundaries. Now, if I had asked you for the year 1965, that would have been perfectly fine to use this for. All right, the next one, actually the last one. The last one I'm going to do, and then you have one to do on your own. All right, this one we're going to do the whole thing again. We're going to graph it, find the best fit line, write the equation, and then use it to make a prediction. So the table gives the amount of time students in a class studied for a test and their test scores. All right, we're going to graph the data, find the best fit line, write the equation. So this is going to be a lot like the first example. All right, so again, this is the last one. We're going to kind of walk you through everything one more time, and then you have one to do on your own. Okay, so first thing we do is we go into the stat plot. We're going to plug that in list 1, list 2. So I'm going to clear out what I have in there. So go to my stats, calculate, not calculate, edit, clear out my list. And then plug in my new value. So hours studied was 103, 1.5. 2.75, 1.5, and 2. And then test score, 78, 70, 92, 89. Calculator slow, so bear with this as I'm plugging it in. Alright, now they're finally all in there. Before I go to graph, I am going to change my window. My previous window was way too big. My time was only between 0 and my highest time would be 3, so I might go up to 5. And then, change that to negative. I definitely don't have to go to 8,000. Alright, I might go to 100. And then scale by like 5. Alright, graph it. See what I already had a line there, but I clear that out. Alright, so graph. So they're kind of all tightly packed up here, so you'll see. So it's not a great linear application, so I bet my R doesn't come out super big. But it kind of looks like it's linear a little bit here. They're kind of like in a slightly linear pattern. So there's my scatter plot. Now the linear equation. So go back into stat. Go over to calculate. Pick 4. My linear regression. And hit enter. Alright. So my R is 0.9. So 0.9 is an okay fit, not a great fit. So it's still an okay. It's better than I thought it was going to be. My slope. So I'm going to give myself like 3 decimal places again. You can go 3 to 4. I'm going to go up 3. So 6.5, 6.7, and 74.355. Alright, so my line is y equals 6.567 if I round 3 decimal places. And then 74.355 if I round 3 decimal. 3 is your minimum. You should at least round 3 decimal places. Don't round any less than 3 unless they tell you to. Alright, is an okay fit. Then the last part is to graph, find the line, write the equation for the line, and then draw it. So let's see how good it fits. Alright, so we're going to go back in here and plug it in. See how good it fits. So 6.567 x plus 74.355. It's not a horrible fit. So you look, see, the points kind of do congregate around this line a bit. So it's an okay fit. It's not a great fit, but it's an okay fit. Alright, now we're going to use it. So we're going to use it to predict. So again, this predictor might be a little off because 3 is my last number. It's not super far away. But 4 is what I'm going to plug in. Comes out to 100 points, so I'm assuming 100 is the max. So they're saying, based on this, if they study for 4 hours, they get a perfect. Again, probably not the best predictor because it is outside my data set. Probably a better predictor would be something within my data set, something between 0 and 3, but there's the predictor that we were asking you for, so there's my line of best fit. Now you're going to do one on your own, so I'll post the answer to this later on. So again, this will ask you to do the whole thing, graph it, find the best fit line, write the equation of the line, then use it to predict. And it should come out a pretty good predictor. Once you do that, go back in here and clear it. So once you're finished with this set, once you're finished with 1.4 and finished scatter plotting, go back into here and turn this off. If you don't turn it off, it might mess up your calculations for the future, for doing graphs in the future. So make sure once you're finished, go in here and turn your scatter plot off. So make sure you turn that off so it doesn't mess with any future graphing. And there's chapter 1. So we're completely done with chapter 1. Then we will do 2 sections in chapter 5. So this quiz is actually over 2 chapters. But chapter 1 is fairly short. And chapter 5, we only covered 2 sections, so I combined them. They're all on linear stuff for the most part, other than the little bit of quadratic we did earlier on. Chapter 5 is going to be doing more stuff with lines. Alright, we'll stop there.